Verification of Einstein model. In 1916, Robert Millikan performed the following experiment in order to disprove Einstein model of photoelectric effect. And what is interesting is, his experiment finally turns out to prove Einstein is correct. The experiment makes use of a photoelectric unit in which there is a color filter so that a very narrow range of frequency of EM wave may enter the photoelectric unit. And inside the photoelectric unit is this circuit, the one that you have seen in the last chapter. The multimeter is used as a voltmeter to measure the voltage across the power supply. So this is the stopping voltage. This is exactly the voltage across the metal plate and the collector. The picometer is used to measure the discharge current. You know, when electrons flow from the collector to the emitter, actually there is current that flow in opposite directions. So the experiment is used to verify the Einstein photoelectric equation. So by measuring the frequency of the incident EM wave and the corresponding stopping potential, then we may be able to plot a graph of stopping potential against frequency. And you can see this is a straight line. And you know why? By rewriting the Einstein photoelectric effect equation, then you may see we may express the stopping potential in this way. And the slope of the graph will be h over E, the Planck constant over the electric charge, while the intercept of the graph will be the negative of the work function over electric charge. Therefore, at that time when Millikan find a straight line graph, and then he find that the slope equals to h over E, at that time he know that he has proved Einstein was correct. So the explanation for photoelectric effect is now completed. In the experiment, it was found that there is a threshold frequency, and now we understand what it is. The threshold frequency is the minimum frequency for the photon to provide just enough energy for the work function of the metal for the electron to be emitted. In experiment, there's no time delay for photoemission, and now we understand why, because photoemission starts as soon as an electron absorbs just a single photon of high enough energy. And lastly, from experiment, we find that the maximum kinetic energy does not depend on the intensity of light. We now know the maximum kinetic energy actually depends on the energy of the incident radiation as well as the work function. Example 6 below make use of the graph on the last page, stopping potential versus frequency, to find Planck's constant and the work function of the metal used. On the bottom left, there are notes that tell you to be cautioned when performing the experiment. Number 1 is that you should clean the oxide that forms on the metal surface. Number 2 is color filter does not allow only a single frequency of light to pass through, but a narrow range of frequencies. Example 7 is a simple demonstration of photoelectric effect using electroscope. And I wonder whether you still remember at the beginning of chapter 1.2, we should start with a negatively charged electroscope in order to perform the photoelectric effect. And now in example 7, the question asks you whether the gold foil will also drop if the electroscope was positively charged at the beginning. And the answer, which should be quite obvious now, is that photoelectric effect would not take place. Photoelectrons would not be emitted. And why? Because even if they were emitted, they will be attracted by the positively charged gold foil immediately. So the photoelectron can never escape. Well, we used to believe that light is a kind of wave. And in this chapter, you can see in some very special case, we have to take light as particle. And we call this the wave-particle duality of light.